Hi, my name is Michael Mühlebach, and today I would like to present joint work with Zhiyu and Mike Jordan. Our work is motivated by the fact that many applications require non-episodic online decision-making in nonlinear continuous state action systems. A typical example is shown on the right. It's a supply chain for a certain type of solar cells. It's an example where we want to develop decision-making strategies to drive up performance in a continuous manner, and we're not allowed to reset the state of the supply chain at any point in time. Now, there's a stark contrast and gap between these applications and the fundamental understanding that's provided in our community. Our works are typically restricted to an episodic or a finite state action setting or to linear dynamical systems. So in this work, I want to show you how we can actually bridge this gap between applications and fundamental understanding. We operate under two different problem settings. The first one is a setting where we have a finite set of models, F1 to Fm. Each model describes stochastic, nonlinear dynamics, and we're assuming realizability. So one of the models in our set accurately describes the underlying dynamics. In the corresponding paper, we relax this assumption, and so you'll be welcome to have a look at it. The second setting we analyzed is a parametric setting where we have a parameter theta that lives in a compact space that's real valued and has dimension p. And similarly, for each theta, we get stochastic nonlinear dynamics. Here's the algorithmic overview. We analyzed a variant of posterior sampling reinforcement learning, and there's three key elements to our decision-making strategy. The first one is certainty equivalence. For each model in the class, we compute a certainty equivalent feedback controller. This can be done offline in simulation, for example, with proximal policy optimization. It can also be done online, for example, with nonlinear model predictive control. Now, as online data comes in, we do posterior sampling over models. We apply the corresponding certainty equivalent feedback control law, and we add additional exploration. The exploration that's added is actually crucial because it enables us to get frequentist policy regret guarantees. This algorithm can also be viewed through the lens of hedge or multiplicative weights. The setting we're in is much more challenging. We have here losses that are not bounded a priori, and we have losses that are statistically dependent over time due to dynamics. And so this is much, much more challenging than the classical online learning analysis of hedge. Here's a numerical example. It's a double inverted pendulum system where we have 1 million candidate models. The learning happens online and in real time. After only about 4 seconds, we narrow down the set of candidates so that we can seamlessly transfer between different non-trivial equilibria. The analysis is highly challenging. We have continuous state actions, we have nonlinear dynamics, a non-quadratic running cost, an uncountable parameter space, and the assumption that enables the corresponding policy regret guarantees is an identifiability assumption. So more specifically, if we have a trajectory of finite length, of length capital M, then we can distinguish between two different models. And the constant CE here, the gap between different models, that has a clear control theoretic interpretation. It's actually related to the controllability of the underlying dynamics. Here's one of our results. It's related to the finite class of models. The assumptions are that we have a cost to go function corresponding to the underlying dynamics in a stage costs that is smooth, feedback policies that are Lipschitz continuous. And if we have this persistence of excitation condition, then we can guarantee a policy regret that scales in the following way. And it's actually a finite sample guarantee. We have precise and explicit expressions for the constant CR1 to CR3. The benchmark that's being considered is the optimal steady state policy under the underlying dynamics. Here's the corresponding result in the parametric setting. Policy regret grows with square root of P, the size or the dimension, of the parameter space, du, the dimension of the inputs, and t, the horizon length. And again, the benchmark is taken as the optimal steady state feedback policy under the underlying dynamics. To summarize, we derived policy regret guarantees for online reinforcement learning on nonlinear continuous state action systems. There's matching lower bounds to our results. We operate under identifiability conditions. The analysis highlights a very powerful separation principle between model identification and control. And I would encourage you to look at the details in the corresponding paper. The algorithms work on challenging examples, including a double inverted pendulum system. We also have ongoing work where we apply this to a real-world soaring robot that soars in a vertical wind tunnel and where there's really challenging aerodynamics. And it's a system where, due to the complexity of the interactions between the system and its environment, we're not able to come up with accurate simulators. And so this is a setting where this online decision-making really shines. Thank you very much for your attention.